Alright, this is a very hard question in my opinion, so let's just get right into it. We have two functions. The first one is f of n, which is 2n plus 1, and the second one g of n is equal to 4n, and we are going to let s be the set of positive integers that can be achieved by applying a combination of f's and g's to the number 0. So what exactly does that mean? Well, let's take a look. If we have f of g of f of 0, for example. So as you can see, we're just applying f's and g's to the number 0. Alright? And let's just calculate it and see what we get. F of 0 is just put 0 in here, so 2 times 0 plus 1 is just 1. So here we get 1. Then we put 1 into g. 4 times 1 we get 4. Good. Then we put 4 into f. 2 times 4 is 8, plus 1 we get 9. And lastly, put 9 into f. 2 times 9 is 18, plus 1 we get 19. And this is the result. You see that this number 19 will be in the set S. So here is the deal. We are going to look for how many positive integers less than or equal to 1024 that are in S. I know I like to do calculus questions a lot and algebra questions, but sometimes this kind of counting questions can be much harder than calculus questions. And I wanted to tell you guys that I actually modified a question from the Oxford MAT in the year of 2020. And that's how I end up with this, for a few reasons. The first reason is that I think this question will be more straightforward. And the second reason is that I didn't want to give you guys the hint that they gave you on the actual MAT, because on the MAT, this question actually has a few parts. And the first part is the biggest hint. So when I take away all that, this question becomes so much harder. And another thing I want to tell you guys that the original question, it says that we will apply f's and g's to the number 1. But right here, I'm changing it to 0 because based on the original question, I wouldn't know if 1 is considered inside of S or not. So that's why I just put it as 0. Then in that case, we can say, okay, when we put 0 in here, f of 0 is 1, and 1 is for sure in S. And when you put 0 in here, we get 0, but we don't care about that because S contains only positive integers. Alright? So, with all that being said, please pause the video and try this first. Now, this is not an easy question, alright? This is not an easy question. Especially if you haven't done a lot of counting questions before. It requires a very different style than like a calculus or plus C, none of that. For calculus integrals, you can put plus C and hope for some partial credit. Like, what are we going to do with this? Right? No. Alright, now let's get serious. So how exactly can we even approach this? I am going to show you guys as much detail as possible, and here we go. Earlier, we have seen that 19 is in S. Okay, that's not bad. We can always just plug in 0 into F first and then just do more of that, F's and G's, and then see what numbers that we get, and then that number will be in S, and then that. But maybe it's also a good idea to kind of reverse it a little bit. In another word, if we look at a number, let's say 100, can we decide that if this is in S or not? Well, in this case, how can we approach this? Well, when we have 100, this right here must came from 4 times 25, meaning that it must be the result of the g function, right? Because f is 2n plus 1. The result of that will be an odd number. So, okay. So, when we have 100, it must be 4 times 25. And 25 is odd. That means it better come from here. And it is. We can look at this as 2 times 12 plus 1. That will give us 25. Good. And then what else can we do? Let's look at 12. 12 happens to be the multiple of 4. 4 times 3, right? So we can write this as 2 times, this right here is 4 times 3, like so, and then plus 1. And then here we have 3. Well, it actually comes from here, f of 1. So we can look at this as 4 times 2 times 4 times 2 plus 2 times 1 plus 1, that's for the 3, and then close parentheses in red, plus 1 like this, all right? And lastly, this one, again, originally the question says we applied f's and g's to the number 1, but here I said 0. So this one, it's okay, you know, it's just f of 0. So this is achievable. Check this out. We can actually write it like this. This right here, 100 is equal to, because the 4 is on the outside, right? So that means it's the very last operation. So we have g, and then that's the f, and then that's the g, and then that part is the f, and then the very inside one is f of 0, which is the number 1. All right, so this is indeed achievable. So that means the number is indeed in S, so that's good. Now, here, let's do another one. How about the number 101? Is this in S? Well, this is odd, so it better come from here. Hopefully that's the case. Well, let's see. This is the same as 2 times 50 plus 1. Sure thing. But how about 50? This is even. Is it from here? No, because n has to be what? A whole number, because you have to start with 0, and the only number that you are going to get is you put 0 in here, you get 1. So all the n has to be whole numbers. So the 50 here, this is not from G, so no, because this is not multiple of 4. And 50, this right here, it's also not going to be from F, because the output of F has to be a number. So as you can see, this right here, it's actually not inside of the set S. Okay, so that's pretty good. But if you just do this like this, then I don't really think that it's going to be any helpful. But if you can do this, let me tell you, get 2 points on the Oxford MAT, because that's exactly one of the parts that I'll ask you to do. All right. But there's one part I haven't told you guys yet, because as I said, the first part is actually like the biggest giveaway, like how exactly you could approach this question. So let's discuss this a little bit. This approach is not nice, because if you do 4 times 25, you get 100. You see so many different digits. It's hard to see a pattern. The problem that we had earlier is that we were doing computation the normal way, and that is in base 10. When we do 25 times 4, yes, you get 100. Of course, we can all do that, but you don't really see a nice pattern in this case. Well, if we move to a very convenient base for this, and that is base 2. Why base 2? Well, if you have ever taken computer science class, then they will tell you computers, they use zeros and ones, and then the computation is very easy. I'll show you. First, have a look. 25 right here. We can write this as 16 plus 8 plus 1. And the 1 is 2 to the 0th power, and then 8 is 2 to the 3rd power, and then 16 is 2 to the 4th power. So in another word, we can write this in base 2, and let's go ahead and do it from right to left. We have 1, 2 to the 0th power, and we have 0, 2 to the 1st power. We have 0, 2 to the 2nd power, and we have 1, 2 to the 3rd power, and we have 1, 2 to the 4th power. So 25 in base 2 is 11001, and usually people put a little 2 right here to emphasize that we're in base 2. And if we multiply this by 4, in base 2, it's as saying we multiply by 100. Aha! This now looks like 11001 times 100. How do we do it? All we have to do is put 2 zeros at the end, And then because we have 1 times this, we can just copy down the number right here. Have a look. If we want to multiply by 4 in base 2, all we have to do is put down 2 zeros at the end. Right? Just attach 2 zeros. So this is what the g function will do. Right? And now let's take a look. What will the f function do if we just look at it in base 2 as well? And let's use 25 again because we have that in base 2 already. So 25 once again is 11001. And for f, we are going to first multiply by 2. So that is just that we are going to multiply this by 10. So this is still very nice because all we have to do is put down a 0 at the end. And then just multiply 1 with all that, which is 10011 backwards like this. But this is not it because we still have to add 1 to it. So let's go ahead and add 1 to it. And again, these are all in base 2. 0 plus 1, we can do that in base 2. It's still just a 1 at the end. And then the rest stays the same, 10011. And have a look. What does the function f do in base 2? Just go ahead and put down the 1 at the end. Attach a 1. That's all. So this is the biggest hint of doing this question. In fact, the part 1 of the actual question that tells you to write 100 in base 2, the binary expansion. And they wouldn't ask you to write 100 in base 2 out of nowhere, right? So that's the biggest hint that this question should be approached in base 2, not base 10. Okay, so that's good, but now we still have to do more though. Now we have the idea that when we apply function g, we just attach 2 zeros at the end. When we apply function f, we just attach a 1 at the end. And let's see what we did earlier, and then maybe we can come up with a nice connection. Earlier, the 100 that we have in base 10, all right? Let's write this in base 2, just like what the actual test will ask you to do. This right here is 64 plus 32 plus 4. Of course, there's other ways to write a number in base 2. Maybe it's much efficient, but 100 is not a big number. This is enough. Alright, so this right here is 2 to the 6th power, this is 2 to the 5th power, this is 2 to the 2nd power. So in terms of base 2, that's right like this. I have no 2 to the 0th power, no 2 to the 1st power. I have 1 2 to the 2nd power, and then no 2 to the 3rd, no 2 to the 4th, 1 2 to the 5th, 1 2 to the 6th. So this is base 2 for 100. And now, how can we utilize this to help us write in terms of f and g's? See, the connection is what we talked about earlier. When we applied g, at the end we have that 2 zeros, and we happen to have the 2 zeros at the end. So that means we must have g at the very end like this. And then when you see the 1, that means we applied the f. And then when we see the 2 zeros, that means we apply the g. And then when we see the 1, that means we apply the f. And then this 1, right? That means we do f of 0. Because this is a modified equation, sorry, so that's why we have f of 0. So it's different than the actual test question. And then close parentheses, close, close, close. Yeah, just like that. So the takeaway is you must see 2 zeros, and then they have to come together, and then 1 can be anywhere. All right. So now let's come back to this. How many positive integers less than or equal to 1024 are in the set S? So how can we approach that though? Now it sounds like a combinatorial question, right? Indeed it is. So maybe you are thinking like this. If you have a 1 all the way at the front, because you always should have a 1 at the front, and then maybe you have several spots. In this case, we have how many spots? 2, 4, 6. 6 spots after the 1. Yeah? So that's 2, 4, 6. So based on this, how can we construct a number that can be inside of S. Remember, because of this, we must have 0, 0 going together. Likewise, the rest is just 1, so the 1 doesn't matter. In fact, if you approach it this way, I will tell you it's kind of hard because how many of these can you put? Can you put 0, 0 here and then 0, 0 here? And then can we put another 0? If so, this has to be 0 as well, because when you put down 0, it has to come in pair, because that's when you apply G, you must produce 2 zeros. So maybe you just put 1 here, 1 here. That works. And how do you do this? Like, you choose how many spots to be 0? No, not really. In fact, I wouldn't know. I don't know how to approach it like this. I don't know how to approach it like this. So what I did is, I'm just going to start from small and then look for a pattern and hope for the best. All right, let's start with the number 1, which is 2 to the 0th power, and there's no spots at the end, right? And that's just one choice. And this right here is in S. That's just f of 0. Good. Now take a look. What if I have 1? The leading number is 1, and I have 1 spot at the end. Then in that case, what can I put down right here? 0? No. The only choice is 1. Right? And this right here, it's the number 3 in the usual sense. Okay, so 3 is inside of S. Good. Continue. If we have 1, and now let's say we have 2 spots. Okay, maybe the last spot right here is 1. Okay, then what can I put down right here? That has to be 0? No, 0 has to come in pair, right? So that means this right here has to be 1. Okay, but if this is 0, what does that mean? That means this right here will also have to be 0. So we have 2 choices right here. And that's all. Good. Now continue. If we have 1 with 3 spots, 1, 2, 3. Okay, so let's see. This time, I'm going to say if we have a 1 right here. In that case, what can we have right here? Can we have 1, 1? Sure thing. But we can also have 0, 0 because we have 2 spots and then just put on 2 zeros. Perfect. Well, we don't need to have a 1 at the end. We can also have this 1 with 3 spots, but maybe this is 0. In that case, this will also have to be 0. Then in this case, what should this be? 1, right? We cannot have 3 zeros. So we have a total of 3 possibilities from here. And now let's do one more. So we have 1, and then with 4 spots now. Suppose we have 1 at the very end. Then what can we put on here? Let's go ahead and just do 1, 1, 1. Good. You can always do 1, 1, 1, or once, that's okay. And maybe we can do 0 here. But in that case, this has to be 0. That means this has to be 1. Or we can also do 0, 0, 1. Okay, so we have 3 choices here. And some of you guys might notice, these numbers look familiar. Alright? And now we can also end with 0. So let's say we have 1 with 1, 2, 3, 4 spots. If we end with 0, that means this right here also have to be 0. And now we have 2 spots. To fill in these 2 spots, we can do what? 1, 1 or 0, 0. Good. So, do we see it? This is actually a very nice pattern. Alright, how many choices do we have right here? It's just one choice. Yeah, the number 1, it's in S. Okay, and now how many choices do we have here? 1. The number 3, it's in S. And now how many choices do we have here? 2. So what are the 2 numbers? This is 4, and the other one is 1 plus 2 plus 4 is 7. So 4 and 7, they are both in S as well. So here we have 2 choices. And then if you look at this, okay, of course we don't have to work out all the numbers, but we have a total of 1, 2, 3 choices. And then if you look at this right here, we have a total of 1, 2, 3, 4, 5. We have a total of 5 choices. And now, do we see it? Do we see it? 1, 1, 2, 3, 5. What's next? 8? Maybe, I don't know yet. Well, let's do one more to confirm, alright? So start with 1, and this time I need to have 5 spots. So let's say 1, 2, 3, 4, 5. So suppose I end with 1. What can I put down right here? In fact, we have 1, 2, 3, 4 spots. If you want to have the 4 spots, just take the possibilities from here, enter it. Look, we can have 1, 1, 1, 1, so that's of course okay. Or we can also have 1, 0, 0, 1, right? That's why I put down right here. Or I can also have 0, 0, 1, 1. Good, but I can also have 1, 1, 0, 0, 1, 1, 0, 0. But I can also have 0, 0, 0, 0. Aha! I do have 5 choices from here. But remember, we can also end with 0. So let's say we have 1 with 5 spots. 1, 2, 3, 4, 5. If we end with 0, that means this right here has to be 0 as well. But now we have 3 spots. Where can we get the 3 spots? Here. Look. 1, 1, 1. 1, 1, 1. 0, 0, 1. 0, 0, 1. And then 1, 0, 0. And they don't violate anything that we said earlier. When you see 0, they come in pair, and then the rest are just ones. And you see this right here is what? 8. We have a total of 8 choices. Aha! So hopefully you can see the pattern of this already. And now all we have to do is just add up all the possibilities. So ladies and gentlemen, this is going to be the answer to this question. Sometimes you like counting, sometimes you hate counting. It's like if you don't know how to count, like if you don't have a systematical way, it's like, oh man, it's like the hardest thing ever. But once you see the pattern, it's like, oh, that's like the best thing ever. I don't know what you think about counting versus integrals. I know I haven't solved the question yet, but let's focus on this. So what I'm going to do is I'm just going to write down all the Fibonacci sequence that we have and then count a few more, and then let's see how many we need. So 1 plus 1 plus 2 plus 3 plus 5 plus 8, and the next one is going to be 13, and the next one is going to be this, and that is 21, and this one is going to be 34, and then 55. Do we need to keep going? No, in fact, this is almost enough, you'll see. So what I mean by that is the following. So let's take a look at this right here. For example, this is 2 to the 0, first, second, third, fourth, fifth power. So this is 2 to the 5th power, which is 32, all right? So check this out. If you want to find out how many numbers less than 2 to the 5th power, then you look at these, right? Look at these, okay? So let's see. This is 8. This is for 2 to the 5th power. Yeah? And then this is 2 to the 6, 2 to the 7, 2 to the 8, 2 to the 9. Yeah. But we want to go to 2 to the 10th power. This is 2 to the 10th power. But if you want to have 2 to the 10th power, what's going to happen is that you just want to consider 1 with 10 zeros. So in fact, this is just that you have to add one more because I have an inclusion right here. All in all, if you add them up, I will tell you the answer should be 144. Before we go, let me tell you about Brilliant.work, where you can learn more about number theory and more interesting mathematics. Brilliant is our sponsor for today's video, and it's an online learning platform with over 60 interactive courses in math, science, and computer science. Go ahead and check out their number theory class because it will help you to build up a strong foundation, which we all know that's the first step to be able to come up with creative solutions to difficult problems, like the one that we did today. especially to learn more about different number systems. They got that for you as well. For their classes, they don't just tell you to memorize the formulas. Instead, they will show you the ideas behind formulas and how to apply them. I'm sure that you will like Brilliant because each lesson has storytelling and fun animations, so you will really enjoy the learning process. And right now, you can even try Brilliant for free for 30 days, or if you use the link in the description, brilliant.world/blackpenredpen, then you can get 20% off discount. I want to thank Brilliant for sponsoring this video, and I also want to thank you guys for checking them out.